All right, so this is the Chapter 8 Notes Part 3, and this will not include the songs. Those will be in a separate video because the songs, when I put them on here, it'll make the track go messed up. So we're going to do straight through notes, and then you can do the songs separately. All right, first concept, standard deviation of slope, also known as standard error of slope, and then standard deviation of residuals. So let's say that I took a sample and my equation of my least squares regression line, my equation of the line that best fits, ended up having a slope of 1.5. So 1.5 pounds per year. So for every one increase in the year, the predicted pounds goes up 1.5. The standard deviation of this slope is 0.25. So what that means is that, another person can get a sample and their slope might be a little bit different. In fact, it might be one standard deviation up. So if their slope is 1.75, that's not going to alarm me too much. That's within one standard deviation of the other information. Same thing with going down like this, so that slope is 1.25. So those are not going to alarm me. About 68% of people's samples will produce a slope within one standard deviation away. And then, of course, we know 95% of samples will produce slopes that are 2 standard deviations off. Okay? So that would take you to a slope of 2, because each time I am adding 0.25. That's a standard deviation of the slope. All right, so what happens is, if I end up getting a equation, if I get data that ends up giving me a slope of 3, I'm going to be alarmed, because that is 6 standard deviations away from my least squares regression line. So that's going to make me worry, and I think I did something wrong or they did something wrong. So that way I have an indication of how close these samples can have their slope to mine. So the words that go along with this, if you are to write them out, are this way. If you sample many times, the slope of the relationship between x and y, the slope of that relationship between x and y will vary about, however much on average. Okay, so if you sample many times, I'd expect the slope you find of the relationship between x and y to vary about that much on average over time. Okay, and it has its own song. All right, next, standard deviation of the residuals. Now, you know that a standard deviation is the average amount that the data is away from the mean. Well, since a residual is actual y minus predicted y, then this standard deviation of the residual is that average amount that the actual y is away from the predicted y. So it's the average amount that the actual y varies from the predicted y. And what's really interesting is we have also that normal model component. So look at this particular example. This right here, this is a residual plot. So this line here is the least squares regression line, or the prediction line of best fits. And so we have a standard deviation of this problem that is 3 pounds. So if I look at my data, if I have 0 residual, then that means I have a piece of data on the line. So incidentally, later we'll talk about x bar is the mean of x and y bar is the mean of y, and this mean of x and mean of y is always on the line. So just a little tidbit is that residual of that point is, if it's on the line, is going to be 0. Okay, so that was just a little side note. But let's take a look at this. 3 pounds. So if I come over here and this is 2.5 pounds up, so I'm going to go like to about 3 pounds up and 3 pounds down. Then that's this information right here. This is all the data, the actual data that is within 1 standard deviation of the prediction line. Well, guess what? That is 68% of the actual y's are within 1 standard deviation. 1 standard deviation of the prediction line, LSRL, least squares regression line. Okay? And so then you're going to see this pattern. If I was to go out 2 standard deviations, that's 6 pounds. So if I was to come out here, that's 5. So here's 6. And here's 6. If I was to come out 6, so within 2 standard deviations is going to be 95% of all of the actual data points are within 2 standard deviations of the least squares regression line, and so on. And then, so then of course, within 3 standard deviations out here is going to be your 99.7% of data. So, in summary, this standard deviation of the residuals tells me the average amount that these actual y's are varying from the predicted, and they fall like the normal model. You know, if you were to think of this as data coming out towards you, if you were to think of this like a normal curve and data coming out towards you, then you have that 68% within 1 standard deviation, 95% within 2, and so on. All right. Next, here on this, this is the second concept that we're doing. And what we're going to do is learn how to take this information here, correlation coefficient and standard deviation and means of data, and come up with that least squares regression line. So come up with the least squares regression line without all of the pieces of data. So how do we do that if we have some different information instead? So let me go ahead, let's introduce it with this problem here. Becky's parents have kept records of her height since she was born, and the data set consists of her age in months and her height in centimeters. So I'm going to say that her age is probably our explanatory variable, and her height is going to be that response, so that will be our y variable. Okay, so here we have the average age, and that's going to be represented by x bar. Because we just have a sample. So this is x bar is the mean of x. So in fact, that's another song that will be on the other video. X bar is the mean of x. And y bar is the mean of y. Okay, and this mean point is always on the line. X bar is the mean of x, y bar is the mean of y, and the mean point is always on the line, Okay, so always on the line. All right, so the mean of the height will be my y bar. This is the standard deviation of age, so that's S of x, and standard deviation of height, so that's S of y. And then the correlation is 0.86. Correlation coefficient represented by the R. So, the first thing that we do to get the equation is find the slope. Step number 1, find slope. There is a formula for that, and it is up here. Slope of the least squares regression line is your correlation, and then this part shouldn't be too surprising. It's your change in y's, or your variation in the y's over the variation in the x's. Just like when you would do slope in Algebra 1, it's the change in y over change in x. So this is the variation in the y's over the variation of x times how well they are correlated. So if I were to fill in all of these numbers with this problem, I would have 0.86, and then I would have the standard deviation of the y's, which is 4.1, divided by the standard deviation of the x, which is 8.5. And I'm going to pause here and go calculate that number real quick for you. All right, so then that slope, when you calculate that out, is 0.41. Okay, so after that, the second thing we're going to do is find the y-intercept. And the way I'm going to do that is I'm going to use a point on the line and this slope. And I'm going to use y equals mx plus b, and I'm going to solve for my y-intercept. Okay, because I have got y bar, that's the mean of y. I have got the slope that I just found, and I've got the x bar, that is the mean of x. So I've got all those numbers that I can fill in, so that's what I'm going to do here. So let's see, y bar is the mean of y. The slope we just found is 0.41. The mean of x is 44. And plus the y-intercept, which I've got to find. So now I'm going to take that 82 and subtract away that 0.41 times 44, and the y-intercept that I get is 63.96. So, in summary, my equation, my predicted y, or I could say the predicted height, is m, which is 0.41, times x, which is age, plus b, 63.96. All right, so that then is the prediction equation. So we could then use that to make a prediction of her height at a particular age. And so here's one more here. So I'm going to let you work on that and as I kind of go through those steps also, so that you can check yourself. So I got 0.17 for the slope. So I get 0.095 for that. So then my equation is predicted y equals slope times x plus the y-intercept. All right, so that's the next concept. So moving on to the third concept of this. Actually, this example 3, I ended up not doing this because if you have all the data points, you're just going to use your calculator, and we're not going to mess with that problem, or example 4. So here we go. The final topic of this is correlate how the correlation coefficient is not affected by any transformation. Your sign may change from positive to negative, but the actual magnitude, the value of it is not, the strength is not changing. So I'm not going to go through all of the specifics of the formula, but the reason has to do with how, commutative property will, if x's and y's switch place, then it does not change the value. And then also if we went through some other stuff, other situations, it doesn't change it. So in summary, since R is measuring the strength, then you can add, you can subtract, you can multiply, and you can divide to all of the data points. So, for instance, all of the x's, you can do something to that, and you could even do something different to all of the y's. And when you do that, the correlation around the placement, the proportionality of all of these points around the line, it could shrink in or it could stretch out, but that it could shift left, it could shift right, but that proportionality does not change, so therefore that R value stays the same. The correlation coefficient is not changed. So you can add, subtract, multiply, divide. You could even switch the x and y. You could switch these values so that you could even switch the x and y, and if you recalculated, the correlation still is the same. The only thing is if you have multiply by a negative. So suppose you multiply x's and you make them into negative x's. Every single problem or every single piece of data you make it negative x's. Then that would change your correlation to the opposite sign. So if you had a correlation of 0.86, that changes it to a correlation of negative 0.86. If you had changed the x's with a negative transformation and the y's with a negative transformation, then that would have made the correlation stay the same, because negative and negative is positive. You wouldn't have had a change on that. All right, so this one has a song as well, and it goes, you can add, subtract, multiply, divide. Well, you can even switch the x and y. Only negative transformations fly, and the R doesn't change. Okay, so that is a quick summary of the lesson related to that. This is page 24, and I'm not going to have you do this problem. You may omit page 24, but on the assignment, I do want you to do pages 25 through 28, and we will complete 29 later. We'll do page 29 later. So for this assignment, I want you to do 25 to 28. I did do this number 2 in class with students, so I'll go ahead and do that again here. So first, this is about cerebellum, and she is in both physics and calculus. So physics and calculus, I don't think that's a necessary, you can necessarily have an intuitive understanding of which one is X and which one is Y. When I looked at the end of the problem, it asked us to predict what her score is on the calculus. So because we were predicting calculus, I chose calculus to be the Y values so that I could predict that. Therefore, physics will be the X values. All right, so then this stuff in the middle gives me all of the data. It says the physics exam scores are approximately normally distributed. The mean of 175, so that's X bar is the mean of X. And the standard deviation of X is 12. All right, the scores on the calculus final are also normally distributed approximately with a mean of 80. So Y bar is the mean of Y, that's 80. Standard deviation of 8. It is also known that the correlation, that's correlation coefficient, between the physics and calculus grades is 0.92. So R is 0.92. So from that, we are supposed to then take a given score on the physics exam. So take a given X and predict her Y. So if we're supposed to take an X and predict her Y, then we need to get the prediction line. Get the least squares regression line to predict her calculus score. So this is that second topic we had covered. The first thing we're going to do is get the slope. Here's the formula. Correlation S of y over S of x. So if I plug that information in, here's what I get. This is a y right there. Comes out to a slope of 0.61. The next step, I'm going to plug into mean of y equals m times the mean of x plus y-intercept, and I'm going to solve for that y-intercept. So I'm going to plug in my numbers. Okay, so if I take my 0.61 times 175, subtract it over to the other side, I get negative 26.75. So in summary, my prediction equation, my predicted calculus score is 0.61 times the physics score minus 26.75. That's my mx plus b equation. And then to finish this out, take your 185 physics score and plug it in. So if I get my predicted calculus is 0.61 times 181 minus 26.75. So given that she got a 181 on the physics, her predicted calculus, and again, that's not guaranteed, it's just what is predicted, so it's important that you have that prediction hat, okay, is 83.66. All right, so that's the last one I wanted to do for you. There are all of your, that's how you do those 3 topics. Now I'm going to make a separate video that has the songs. There are 3 of them that go along with this information, and that will be listed separately.